Hello friends, and welcome to our video lecture on topic S2.2 covalent structures. We started S2.2 a little bit in our last video lecture. We are going to dive more into determining the covalent nature and properties of substances. These are our content statements. And these are our objectives. We're going to talk about VSEPR theory, that's valence shell electron pair repulsion, which allows us to predict molecular geometry and bond angles of molecules. We're going to talk about the polarity of bonds and the polarity of molecules, which aren't necessarily the same as that bond polarity. We're going to talk about some exceptions to molecular compounds, covalently bonded network solids. An example will be the allotropes of carbon. We're also going to talk about the super weird coordination bonds. And we're going to start off with some VSEPR theory. This again is valence shell electron pair repulsion. We know that because electrons are all negatively charged, they will repel each other. And so when we're looking at the shape of molecules, we're just trying to spread those electron clouds out away from each other as much as possible because they're going to repel each other. So how we predict the shapes of molecules, we're going to start with our Lewis dot structures. We talked about these a little bit in our last video lecture. How we draw a Lewis structure, we're going to count the number of valence electrons available for bonds. Carbon has 4 valence electrons, oxygen has 6, but there's 2 of them, that adds up to 12, plus 4 is going to give us a total of 16 electrons. We're going to put the carbon as our central atom because it can make more bonds than can oxygen. We're going to put oxygen around the carbon. We're going to start by putting pairs of electrons between our atoms. So there's 2 and 4. Now we're going to distribute the rest of the electrons so that everybody has an octet. So again, we had 2, 4, here's 6, 8, 10, 12, 14, 16, and I have run out of electrons. And this is bad because oxygen here only has 6, carbon here only has 6. This is a problem. So what we're going to do is make some double bonds. So I'm going to go ahead and take that pair away. I'm going to take that pair away. And then we're going to make these guys some double bonds. So if I put another pair of electrons here, another pair of electrons here, now all of our atoms have a full octet. So oxygen here has 8, carbon in the middle has 8, oxygen here also has 8. So now to predict the shape of this molecule, we're going to think about how we can spread out those valence shell electron pairs. What is the best way to get these 1, 2 groups of bonding electrons as far away from each other as possible? Well, that's going to be a line. So we're going to put oxygen here, we're going to put oxygen here, we're going to put carbon in the middle, and let me choose a better color so you can see that. And then, of course, we're going to have not single bonds, but double bonds in here. But that doesn't matter. What matters is that it's a bonding group. Bonding groups can be single or double or triple. We want these bonding groups to be as far away from each other as possible. And so we make a line, and we call this molecule linear. The shape of this molecule is linear. The shape of carbon dioxide is linear, and its bond angle, because it's a line, is 180 degrees. Good. All right, let's do another one. And let's take a look at boron trichloride. Boron has 3 valence electrons, chlorine has 7, there are 3 of them, so that makes 21. 21 plus 3 from boron gives us 24 total electrons to put into our bonds. What should be our central atom? We're going to choose boron because our halogens can only make one bond. They are never going to go into the middle. So we've got boron and we've got chlorine and chlorine and chlorine. We're going to start by putting pairs of electrons between our atoms. We've got 2 and 4 and 6. Now we're going to distribute the rest of the electrons around atoms so that there are some full octets. 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh no, boron only has 6. Should we make a double bond with chlorine? No, because this is one of our weird exceptions Boron is okay with an incomplete octet. So 6 is better than 3 for boron because boron is not super non-metallish. It's just barely a little bit. We're going to just let boron have 6. Chlorine is absolutely not going to make double bonds with boron. So what are we going to call the shape of this molecule? We have 1, 2, 3 groups of electrons around our central atom. So the best way to spread out 1, 2, 3 groups is to make a triangle. And so we're going to put these guys into a triangle where I've got chlorine and chlorine and chlorine and boron here in the middle. These electrons are spread out as much as they can be spread out, and our bond angles are going to be 120 degrees. We're going to call this trigonal planar because it's a triangle, right? And it's flat. Plano in Espanol is flat. So planar, here we have a trigonal planar shape. It's a flat triangle. We're going to talk about a different triangle that's pyramidal in a little bit. This is our flat triangle. Get excited for a pyramidal triangle. But first, let's talk about ozone. So O3 is ozone. We have 3 oxygens. Each has 6 valence electrons. There's 3 of them. That makes 18 electrons. It's all oxygen, so it doesn't matter which oxygen we put in the middle. It's going to be all oxygens. Let's put those pairs of electrons between atoms. There's 2, there's 4. We're going to distribute around the rest. We've got 6, 8, 10, 12, 14, 16, 18. Oh no, we have run out of electrons. We are going to make a double bond in this instance. Oxygen will absolutely make double bonds, especially with itself. So I'm going to take away one of the pairs and I'm going to make it a double bond. And so now what we have is oxygen with 8 and oxygen with 8 and oxygen with 8 electrons. Everybody's got that full octet. Let's look at our shape now. This one's a little bit different from the last 2 that we looked at. We have this one group of bonding electrons. We have this other group of bonding electrons. But this one's a little bit different because now I have a group of non-bonding electrons. Sometimes we also call these lone pairs. These lone pairs of electrons also repel the electrons that are in the bonding groups. So in this case, we have 2 bonding groups and 1 non-bonding group of electrons. That means that there are total 3 things around that central atom. And so our shape is going to once again be trigonal planar. So I have a 1 and a 2 and a 3 around that central atom. Of course, we've got bond and double bond and electrons, but those 3 things around the oxygen are going to repel each other. And so we have an electron domain shape of trigonal planar. This is our electron domain shape because it includes that non-bonding pair of electrons. But what about the molecular shape? What if I don't want to talk about the shape of the electrons? I just want to talk about the shape of the molecule. Well, we're going to call it this guy bent. It's bent. So our non-bonding pair of electrons is here. They're taking up space, repelling the electrons that are shared here and here. Our shape is bent. It looks from this picture like it could be linear, like carbon dioxide. It is not. It is bent. And our bond angles, here's another quirky thing. Looks like it should be 120 degrees, right? Because it's trigonal planar in its electron domain. But these non-bonding pairs of electrons, they've got a little bit more freedom than do these shared pairs of electrons, and so they take up a little bit of extra space, which means that these guys get pulled together a little bit. And so instead of having 120, it's just a little bit closer. It's like 117 degrees. And then, of course, This has got that little bit of extra space. So our molecular geometry here is bent. Our electron domain geometry is that trigonal planar, and this is ozone. How about some carbon tetrahydride? When we get to our unit on organic chemistry, we're going to learn that this is also called methane. So this carbon tetrahydride, or methane, let's talk about its valence electrons. You've got carbon has 4. Each of these hydrogens has 1. There are 4 hydrogens, so that makes 4. 4 plus 4 is 8 total electrons. Hydrogen never, ever, ever goes in the middle, so definitely carbon is going to be our central atom. We're going to put the hydrogens around the carbon, and then we're going to put our shared pairs of electrons between. There's 2, there's 4, there's 6, there's 8. There's 8. We have run out of electrons. Is this a problem? None of the hydrogens have 8. Of course, this is not a problem. Hydrogen cannot have 8 because it only has energy level number 1. There's no space for any more electrons than 2. And so this is going to be our Lewis structure for carbon tetrahydride, also known as methane. Let's talk about the shape. So we've got 1, 2, 3, 4 bonding groups of electrons around that central atom, that central carbon. It would be tempting to make like a plus sign and say that these guys are going to spread out to be 90-degree angles. And this is the best that we can do to spread out those groups of electrons. Except molecules are three-dimensional, and so we can actually push some back and pull some forward, and we're going to end up with a shape that looks a little bit more like this, a little bit of a pyramid with this thing on the top. And this is called tetrahedral because on my central carbon, there's 1, 2, 3, 4 legs. And to spread them out evenly in three-dimensional space, we're going to end up with bond angles of 109.5, 109.5, here 109.5, and here 109.5. So this will be symmetrical in three-dimensional space. We can flip it around and around and around, and we're going to end up with bond angles of 109.5 between all of those atoms. So be careful. Do not get stuck in two-dimensional thinking. Remember that we can have three-dimensional molecules. The shape of carbon tetrahydride, also known as methane, is tetrahedral with bond angles of 109.5. Our next example is NH3 nitrogen trihydride, also known as ammonia. So let's look at our central atom. Do we like nitrogen or hydrogen for the middle? Of course, we do not like hydrogen. We like nitrogen for our central atom. We're going to put our hydrogens around. I'm going to go a little bit different pattern this time and put the hydrogen on top instead of on the bottom, which I usually put it on the bottom. It doesn't matter because remember that these molecules are three-dimensional. I'm going to count up my valence electrons. Nitrogen has 5. Each of those hydrogens has 1, but there's 3 of them. That makes 8 total electrons. We're going to put our electrons between the atoms in pairs, 2, 4, 6. I have one more pair. Should I give it to a hydrogen? Oh no, hydrogen is perfectly stable with just those 2 electrons. I'm going to give that final pair to nitrogen. So now nitrogen has those 8 valence electrons. Each of the hydrogens has 2. This is perfect. Let's talk about the molecular shape. So on the nitrogen, we have 1, 2, 3 bonding groups of electrons. We also have 1 non-bonding group, 1 lone pair of electrons. This means that the total count of electron groups around the nitrogen is 4. 3 bonding groups and 1 non-bonding group. 4, that's our prefix tetra. So what's going to happen is the electron domain geometry, when I'm also counting these lone pairs of electrons, is going to be tetrahedral. But if I want to look at just the molecular geometry, where I'm not counting those non-bonding pairs of electrons, even though they're still there, we're going to end up with, I promised you there would be another triangle. Here it is. We're going to call this trigonal because it's a triangle from those 1, 2, 3 hydrogens, but now it's going to be pyramidal. Because what happens is, here's our hydrogen and hydrogen and hydrogen, here's our nitrogen. The electrons that are here, our non-bonding pairs of electrons, are actually going to repel and push those hydrogens down just a little bit, making them a little bit of a pyramid instead of a flat or planar triangle. Now we have a pyramidal triangle. How about those bond angles? Well, this is tetrahedral. Our tetrahedral bond angle is 109.5 degrees. But, like we talked about with the ozone molecule, these electrons take up just a little bit more space. They have more freedom to move than do the electrons that are caught in the bonds. And so those electrons, our non-bonding pair of electrons, are going to push our 3 hydrogens in just a little bit. And instead of a 109.5, we're going to end up with a little bit smaller, because these electrons are pushing, we're going to end up with bond angles of about 107. So bond angles of just about 107 degrees, definitely going to be less than 109.5. So sometimes we go ahead and pick a number. Sometimes we're just like, meh, it's just going to be less than that 109.5 that we have in a typical tetrahedral molecule. All right, let's do another example. And of course, no chemistry lecture, or biology lecture for that matter, is complete without talking about water. So let's pick our central atom. It's never, ever, ever going to be hydrogen, so it must be oxygen. We're going to put oxygen in the middle, hydrogen and hydrogen. We're going to count up our valence electrons. Oxygen has 6, each hydrogen has 1, but there's 2 of them. So 2 plus 6 makes 8 total electrons that we can put in these bonds. We're going to give 2 between these 2 atoms, 2 between these 2 atoms. Should I make some double bonds between the oxygen and the hydrogen? No, because hydrogen is stable with only 2 electrons. It's in the first energy level. There's only that S sublevel. There's only 1 orbital. 2 is as good as it gets for hydrogen, which is actually quite good for hydrogen. And then we're going to put those last 2 pairs of electrons, the last 4 electrons are just going to go on the oxygen. So you might be thinking, haha, this is going to be linear just like carbon dioxide because there is 1 and 2 atoms, and so the best way to spread them out is to make a line. But my friends, don't forget about those lone pairs of electrons. These guys take up space. These guys are also repelling those bonding groups. So if we count all of the electron domains around that central oxygen, we get 1, 2, 3, 4 total groups of electrons, 2 bonding pairs, 2 non-bonding pairs around that central oxygen. That's 4 groups of electrons. 4 is tetrahedral. Our electron domain geometry is tetrahedral. It makes a little bit of a pyramid where we have oxygen and we have electrons and we have electrons and we have hydrogen, and then we have hydrogen going back in space. So tetrahedral is our electron domain geometry. But if I'm looking just at the molecular geometry, our molecular geometry, where I only care about where the atoms are, the hydrogen, and the oxygen, this guy is also bent, like ozone, but also not like ozone, because let's talk about our bond angles. So because it's tetrahedral, we're going to start at about a 109.5 degree bond angle, because we had these 1, 2, 3, 4 things around that central oxygen. But in fact, remember that these non-bonding groups of electrons have more room to move. They have more freedom to move than do our bonded electrons. So these guys are going to push. And just like in ammonia, they're going to push. And so we're going to end up with a bond angle of 107, except, you know what? There's not just 1 lone pair of electrons. There's 2 lone pairs of electrons, which is going to push even a little bit closer. So it's not going to be 107. It's going to be like 104.5. 104.5 degrees is going to be the bond angle between the 2 hydrogens in our water molecule. So it's not just less than 109.5, it's less than 109.5 degrees. And we're still going to call it bent, but remember that in ozone, ozone had that one non-bonding group and then those two oxygen bonded groups. So this was 1, 2, 3, and so we went with less than 120. This was about 117 degrees. So this was bent coming from trigonal planar. If I'm starting at tetrahedral and I end up bent, the bond angle is going to be 104.5. Because again, we've got one bonding group pushing, we've got another bonding group pushing. Oh my gosh, I just called them bonding groups. No, these are the non-bonding groups. So sorry, my friends. The non-bonding groups pushing on the bonding groups. The bonding groups are here and here. Feeling good? All right. And here's a lovely summary of all the shapes that we need to know. So the steric number, the number of groups, total groups of electrons around our central atom. So if there's 2, like in carbon dioxide, then we're going to end up with a linear shape. Those 2 groups of electrons, of course, maybe they're double bonds. That's okay, as long as the bonding groups are only 2 and there are 0 lone pairs, we're going to have a linear shape, and that's going to be a bond angle of 180 degrees. If I have 3 total groups of electrons and 0 lone pairs, kind of like our BCl3 boron trichloride, then we're going to end up with a trigonal planar shape, bond angles of 120 degrees. But if I do have 1 lone pair in that trigonal planar molecular shape, then we're going to end up instead with a bent shape where there's electrons here and then atom and atom bonded here. Our shape is going to be a little bit less than 120 because this electron pair is freer to move a lot. And so we're going to end up with bond angles of less than 120, maybe about 117. What if I have 4 total groups of electrons around our atoms? If, again, there are 0 lone pairs, then we're going to end up with a tetrahedral shape. This is like carbon tetrahydride or methane, where we've got our central carbon, 1, 2, 3, 4 atoms are bonded, bond angles of 109.5. But if I do have 1 lone pair, then we're going to end up with what we call trigonal pyramidal instead. We're going to have our triangle here, but then because of that lone pair of electrons, we're going to push that triangle down into a pyramid shape instead of, like we had here, our flat shape. Our bond angles are going to be not quite 109.5 because this lone pair of electrons pushes a little bit more. And so we're going to end up with less than 109.5, maybe about a 107. This is like ammonia and H3. And then water was the last one that we looked at. Here's our water molecule where we still have those total 4 groups of electrons around the central oxygen. But now we have 2 lone pairs of electrons. Lone pair of electrons, lone pair of electrons. So still 1, 2, 3, 4, but now my 109.5 is going to get a little smaller and a little smaller again. We're going to end up with bond angles of about 104.5 between, here's our oxygen and hydrogen here, because we have, again, those 2 groups of non-binding electrons pushing a little bit extra on the bonds between the hydrogens and the oxygens. There are more shapes that we don't need to know. So for us in Chem SL, this is all we need to know. If you are in HL Chem or you're getting ready for college chemistry, here we have some of our expanded octet exceptions to the rules. Think about this central atom A. If 8 is great and this guy's got 2, 4, 6, 8, 10, what madness. So just like boron was an exception with fewer than 8, there are lots of exceptions with more than 8 electrons. So these expanded octets we do not need to know for us in SL Chem, but it's not a bad thing to know that they exist. We're going to look at one more little shape before we jump into some polarities. So just like our non-bonding groups of electrons, so when we had ammonia and H3, the non-bonding group here, we talked about how it is a little bit freer to move. It's going to take up a little bit more space. Interestingly, when we have double or triple bonds in our molecules, they also take up a little bit more space. So this is formaldehyde or methanal. So be careful, it's not methanol, it's methanal. And its Lewis structure is going to be carbon. It's going to be double bonded to the oxygen. And then we're going to have the two hydrogens, of course, single bonded because hydrogen is never, ever, ever going to make a double bond. So it looks like this guy is going to be trigonal planar because we've got 1, 2, 3, even though it's a double bond, it's a single bonding group. We've got these 3 bonding groups around our central atom. This should be trigonal planar. And it is. And we would expect to have bond angles of 120, except because we've got this double bond up here. The double bond between the carbon and the oxygen. Here's our oxygen, here's our carbon. Because there's not just 2, but 4 electrons in here, they do take up a little bit more space than do our single bonds. And so our bond angle is going to be just a little bit smaller. This is going to be closer to 116. These will be closer to 122 because, again, this oxygen double bonded to carbon, these 4 electrons are going to take up a little bit more space than the 2 that we have here and the 2 that we have here. So just like our non-bonding pairs of electrons take up a little bit more space in the molecules, so do double and triple bonds. We're going to put VSEPR away for a little bit and look at some bond polarity. You need table 9 in your data booklets. We're going to be looking at the electronegativity differences of atoms in bonds because this is how we know if bonds are polar or not. Remember from our last lecture that the cutoff for us in IB world is a 1.8. So if your electronegativity difference is greater than 1.8, we're going to call you an ionic bond. Whereas if your electronegativity difference is less than or equal to 1.8, we're going to call you a covalent bond. Of course, the bigger the difference, but still less than or equal to 1.8, the more polar you are, the smaller the difference, the less polar you are, unless you are a 0 difference, in which case you are a pure covalent or purely nonpolar covalent bond. Let's look at some examples. We've got HF, hydrogen fluoride. If this was dissolved in water, we would call it hydrofluoric acid. So hydrogen's electronegativity difference is 2.2 and fluorine's is 4. The difference is 1.8. Oh my goodness. We are right at the top edge of being covalent. This guy is so polar. So the electronegativity difference is going to be 1.8, which is as big a difference as you can have and not be ionic. And so this guy is going to be very polar. And we can show the polarity with some vectors. So we're going to draw an arrow, a little line through it. That tells us it's a vector. And this is just showing us that those electrons are getting pulled more closely to the fluorine than they are getting pulled to the hydrogen. And that shows us that we've got a partially negative side of this molecule. And then what's left over with hydrogen is partially positive. We use that sigma Greek letter to show partial charges due to polarity. Let's do water. So water, hydrogen again is 2.2, oxygen is 3.4. Now we're not going to add together the 2.2s because we're looking at each bond by itself. So 3.4 minus 2.2 is 1.2. 3.4 minus 2.2 is also 1.2. So each of those bonds individually is quite polar. Not quite as polar as 1.8, but also pretty polar. And so we can draw our vectors to show that we have electrons getting pulled toward the oxygen. And this is just, again, showing that we've got more negative on the oxygen side, and then each of our hydrogen sides is going to be partially positive. Let's look at carbon tetrahedride. So carbon's electronegativity is 2.6. I'm going to pick a better color that you can see. 2.6. And then hydrogen is going to be, again, 2.2, 2.2, 2.2, 2.2. Again, we're going to look at each bond individually. So the difference here is 0.4, and here is 0.4. Here is 0.4, and here is 0.4. So we do have very barely polar bonds because it's not a 0 difference. So a little bit of polar bonds here, and we're going to draw our vectors pointed toward our carbons. Good. All right, one more. Let's look at just a hydrogen gas molecule. Hydrogen is 2.2 and 2.2, and the difference between 2.2 and 2.2 is 0. Of course it is, because it's the same atom. And so this one is going to be a purely nonpolar covalent bond. Let's look at how these polar bonds can make molecules polar or not. So we decided that with hydrogen fluoride, we did have that vector showing the electron pull more toward the fluorine side of the molecule. We have a partially negative charge on the fluorine, partially positive on the hydrogen. This overall pull of the electrons to one side of the molecule makes this one side a negative pole, and this side is a positive pole, and because those poles are different, this is a very polar molecule. When we look at water, we have a similar story. So we have those electrons getting pulled toward the oxygen. We have a partial positive on our hydrogens. Interestingly, because we have those non-bonding pairs of electrons on the oxygen, we have even more vector movement toward those non-bonding pairs of electrons. And so if we are to sum our vectors, which is a very physics thing to do, but we're going to do it in chemistry as well, if we look at the overall direction of these vectors, we're going that way, which means that I have a pole on one side and a different pole on the other side. Water is also quite polar. Let's look at methane, because we're about to blow our minds. Are we ready? So we know that we've got these just barely polar bonds in the middle of the methane molecule. But if we sum up our vectors, look how direction-wise they cancel each other out, because this molecule is beautifully symmetrical, because the outside of the molecule is all partially positive and the inside, which doesn't count, is not. Then, oh my goodness, we have here a non-polar molecule. Even though there are polar bonds, the molecule is non-polar, because it's so beautifully symmetrical, because we do not have an asymmetrical distribution of charge or electrons. We've got us here a non-polar molecule. And then of course the hydrogen, because it doesn't even have any polar bonds, is going to also be a non-polar molecule. Let's look at just two more examples of molecular polarity. So here I'm looking at carbon tetrachloride. Oh my goodness, the electronegativity difference between chlorine and carbon is huge, and our vectors are going to be pointed so much in the chlorine direction. Those bonds are very, very polar bonds, but because we have a symmetrical distribution of these partial charges, all of these guys around the outside of the molecule are the same. We do not have an overall pull in any one direction. Our vectors sum out to 0. They're all canceling each other out. What this means is that our molecule is non-polar. So we have some hugely polar bonds, but our molecule is totally non-polar. What if I switched up one of those chlorines for a hydrogen? So now we're going to switch this vector and make it go that way instead. The polarity here is not as strong as the polarity here, so these vectors are going to be quite a bit longer. But now when we sum up our vectors, notice that the overall pull is going to be downward. And so we're going to have this side of the molecule be negative, and this side, which we turned into a hydrogen instead of a chlorine, is going to be positive. And now I do have a quite polar molecule. So be careful. If we've got this beautiful symmetry around the outside of a molecule, we're probably going to have a nonpolar molecule, even when we have polar bonds. Whereas here, I don't have that symmetry. This guy is different from these guys. Now I do have polar bonds and a polar molecule. We're going to look at a few exceptions to the idea of covalently bonded molecules, and then we're going to wrap up our day, my friends. So covalent network solids, these guys are covalently bonded. They are sharing electrons. These silicon atoms are sharing electrons, but they form lattices just like the ionic compounds that we talked about in our last lecture. So here we have sodium chloride. It's an ionic lattice where we have oppositely charged ions that are attracted to each other in a three-dimensional space. We can also have covalent lattices. So these guys are not ionic. We don't have any ions here between the silicon atoms. Instead, though, we do have sharing of electrons between atoms in an undefined, indeterminate number going on potentially for a long time. But we're sharing electrons in this three-dimensional space. We're not transferring electrons. We don't have any ions. But because of this lattice structure, we do end up with much higher boiling points and melting points than we usually have in our covalently bonded molecular compounds. We also end up with some super interesting properties. This guy, SiO2, notice that we have 4 oxygens for every 2 silica, and so we're going to silicon atoms, sorry. So we have SiO2 here. This is basically sand or glass or quartz. Definitely not the typical covalently bonded molecular compound. Instead, we call these guys covalent network solids. So they're covalently bonded, but they form a lattice. Crazy high melting points and boiling points, quite different from most of our molecular compounds. One more example of these covalent network solids are allotropes of carbon. So these 3 substances are all just carbon, but what's cool is that they take different structures and therefore they have different properties. And this is what we call allotropes. So allotropes are different structures of the same element. Carbon has several allotropes. We're going to look at a few of them here. So fullerene is super cool. This one is actually a molecule, but it's a really big molecule, usually 60 carbon atoms covalently bonded to each other. And so they make these ball shapes. Sometimes we call them Buckminster fullerene because Buckminster Fuller was the guy who kind of discovered them. They are geodesic in shape, and sometimes we use these guys to deliver medicines. We can throw other molecules into the middle of these little molecule balls, and then they can go deliver medicines or whatever to wherever we want to send them. Diamond is also just carbon. Interesting about diamond. So we have 1 carbon bonded to 1, 2, 3, 4 other carbons. This is going to give diamond a super strong, very stable 3-dimensional solid shape. Quite crystalline, of course. Graphite is similar. So graphite is different from diamond in that it is carbon bonded to only 1, 2, 3 carbons instead of 4. We know that carbon has a valence of 4. We should have 1 more bond in there. And so what actually happens is sometimes we pretend like there's a double bond, but in reality, we've got these electrons that kind of get shared between those 3 bonds. Those electrons, because they're not stuck in one spot in the molecule, we call them delocalized. So they are delocalized electrons. Delocalized electrons can move. And if we have things that can move, then they can conduct electricity. And so graphite can actually conduct electricity in a way that diamond cannot because of these delocalized electrons. What's super cool about graphite, this is what we have, our pencil lead is actually graphite, not lead at all. Thankfully, because that would be awful if we had all of us exposed to that much lead all day, every day at school. So what we can do with the graphite, they are these 2-dimensional sheets of these carbon atoms bonded to more carbon atoms. And then there's some hydrogen bonding. We're going to talk about what that is in our next lecture. This force of attraction that holds these sheets together, but these are not actual chemical bonds. They're just forces of attraction. And what that means is that we can actually peel these layers away from each other. And if I take just 1 layer, so now I have this 2-dimensional layer of graphite, just 1 sheet, now we're going to call it graphene. And that's a super cool compound that scientists are doing amazing things with. And just one more exception to our typical molecule shapes. We're going to look at coordination bonds. Sometimes we call these dative, but that's an older name. So coordination is a much better vocabulary term here. What happens in coordination bonds is that the electrons are not being donated by the atoms equally. So here we have carbon monoxide. Carbon has 4 valence electrons, oxygen has 6. That's a total of 10 valence electrons. So when I put these electrons into the bonds, we're going to start with our pairs between the atoms. We've got 2, we've got 4, we've got 6, we've got 8, we've got 10. Oh no, carbon does not yet have even close to 8. And so what we're going to do is take some away and make a double bond. We're still not there. We're going to take some more away. Notice that I'm taking away again from oxygen, and we're going to make a triple bond here. Oxygen donated more electrons to this bond than did carbon. So in this picture, we're showing oxygen's electrons with circles. Carbon's electrons are the X's. Notice that in my triple bond, I have 2 pairs coming from oxygen and only 1 pair coming from carbon. When we have one atom that is donating a whole entire pair all by itself to the bond, we call those coordination bonds. Or dative bonds, but coordination is better. They're weird, they're unusual. And so on that note, my friends, we are going to wrap up this video lecture. We accomplished all of these objectives. We did so much practice on VSEPR theory. We're going to do lots more in class. We talked about bond polarity and how it is related but not always necessarily indicative of molecular polarity. We talked about our covalent network solids, the silica, the SiO2, sand, quartz, glass, weird stuff. We talked about those allotropes of carbon, which most were also covalent network solids, the graphite, the diamond, and those coordination bonds where we have one atom donating more electrons to the bond than the other atom. Great work today, my friends.